So something that I just
okay. Yes. Okay, welcome to the second lecture with a little delay. The academic quarter, that's fine. So today we're going to look at how to implement a very basic proof checker. I would say it's not very helpful. I would hesitate to call it an assistant. So we're going to, the title is a monadic type checker because there's one thing I'd like to emphasize, which is that that we should start paying attention to computational effects, which in today's lecture will be embodied by a monad. And then there are going to be more computational effects tomorrow and even more on Friday. But today's computational effects will be quite small. There we go. So lecture 2, we're just simply going to look at how to implement the thing we did in lecture 1. And so there are some components, and we are going to go to them. Okay. So you could divide up the tasks in the following way. We need a parser, so that's something that converts the strings typed by the user into something more abstract. It gets you up a couple of levels in the hierarchy that Andrej helpfully drew on the board in his first lecture. So this is standard technique. Roughly speaking, there will be 2 steps. There is a lexical analysis and the parsing. I'll come back to them. I'm not going to elaborate on them now. This is just an overview. Then the core of what we're doing is something that will be able to do inference and checking. So an implementation of the bidirectional algorithm. And of course, it also has to be equipped with normalization and equality checking. And then everything is packaged together by top level that can process command line arguments and some top level arguments that just allows the user to interact with the system. I should say, I'll say more about these things when we come to them. So let's just start with, so we could go this way, but there's another way to frame what we're doing, which I think is also helpful, which is in terms of data types that we need. So we can think ahead to say, okay, each of these things is going to work with some data types. What are they? So obviously we have input strings. Those are just strings. There is one little interesting thing to say about strings, which is UTF-8, right? If you want to support UTF-8 in OCaml, you have to not be completely naive. And then the lexical analysis produces tokens, but that's the kind of thing that will be done for us by the parser generator. I'm just saying that is one of the data types. The things that we do have to do that are our responsibility is we have to define a data type that will represent the input in terms of a syntax tree. So that's something we need to define. We would like it to record file locations. So we want the parser to insert file locations into these trees so that when we find an error, we can report to the user where the error was. So that's one reason that's why we want file locations to be there. We want the variables are still just strings. So the parser will say, here's a variable, we just store it as a string. We don't do anything at this level. This is just to suck in the input. Okay, so I'll call this the input syntax or the syntax trees. And then there is an internal representations of terms and types. Now that one is not going to have any locations because these will be terms and types that were already type checked. Therefore, they are correct. So they cannot be the cause of any error. So there's no point in having locations. Also, it gets kind of tricky to figure out what locations to use anyway, because maybe you do a substitution and then with respect to the input, everything looks different. So it doesn't make sense to do this. And at this point, we do want support for bound variables and substitutions. We don't actually do any substitution on the bare input stream, the bare input syntax. But here for normalization and so on, we need to be careful about bound variables and substitution. And then, of course, there needs to be some sort of a data type for contexts. And this one is going to map, we'll come to it, but it will have two components. One that maps the strings to the abstract variables, and another one that maps abstract variables to their typing information. Okay? So let me not start a religious war. We're going to implement this in OCaml. And even before I show this slide, somebody already asked me, can I do this in Haskell? Yes, it's Turing complete. So sure, you can do it in Haskell. There's no, I mean, in fact, I think it would be an interesting exercise to do it. If Haskell is your preferred language, you could, for instance, take this in this and say, oh, I'm going to make it a lot better. And then you can maybe like shorten it by 30% or something. But anyhow, why OCaml? Well, first of all, we are in France. I think that in itself is a good reason. But also there are lots of serious tools that are implemented in OCaml, some of which are presented in Frederick's lecture, Deducti, Lambda Pi. So that's, you know, it's got, we know that it should be possible to do it. It's got quite good developer environment, which has gotten really good in the last years, much better than it used to be. And there will be some libraries that we will use, the Lexer, the parser generator, and I will use bindlib to manipulate bound variables, because that's not something that I want to do with my bare hands. I was said here, I was going to post and say I will use bindlib because Lambda Pi uses it. But I was told by Frederick over lunch that Lambda Pi doesn't use it anymore because it's not good enough for them. It's going to be good enough for us. I should say that people stress so much. First of all, people stress a lot about bound variables. There's something called Popple challenge, which is to implement the meta theory of syntax with binding, and this is an ongoing thing, and you can always go. But there are people who never get tired of this topic. There are reasons for this, but also I think it's really a critical part of your implementation, because this is something that your proof assistant or proof checker will do all the time. All the time, it's handling bound variables, free variables, performing substitutions, and so on. And so that's a critical component in terms of efficiency. If you do your own naive De Bruijn index, homemade implementation, it's going to work okay, but it's not going to beat Lambda Pi speed or any of the real things. Okay, let's go on to parsing. So I'm not going to spend too much time, since so many people raise their hands when they ask who has used the parser generator. But nevertheless, just so that we're all on the same page, let me give you a quick overview of how parsing works. Okay, so there are two steps. The first one is lexical analysis. And the task of lexical analysis is to break up the input string into something called lexemes, or they are just little substrings, and then map them to something slightly more abstract, which is just a symbolic representation of these substrings called tokens. The lexemes are described by regular expressions, and the tokens are defined in the parser, the description of the parser. With some luck, if I click on this, we should be able to see some of these regular expressions. Here are my zoom attempts. Okay. So down here, you will start to see some regular expressions. Underscore, punctuation marks, arrows, mysterious UTF characters that look like arrows, and so on. So then there's prefix and infix operators. We're going to use the OCaml convention for infix operators, just to make things easy. A nice exercise to pretend to be Agda is not too complicated, but I thought that's an unnecessary complication for these lectures. And then there's some reserved words, which are up here, and they're also just regular expressions. You can go through this in your own time. So just regular expressions, that's my point. There's some description of how to break up your strings into pieces. And then there is the description of the grammar, which is a file. This is a menhir. This is the menhir parser generator. So see, it defines a bunch of tokens. And so, for instance, if we go and look, we have the underscore regular expression. This thing is here just so that line numbers are counted. It said this is underscore. So it's that one. Okay, wherever it was. Here. Okay. And down here, there are grammar rules that say what's what. And so the general idea is that, for instance, if we look at, let's look at terms. So it says a term can be either an infix term, which is down here, or a product, or an arrow, or a lambda, or a let, or something colon something. Then you go and you look, and this is just a grammar that's constructing syntax trees. And the syntax trees are described somewhere. And it's going to be, the syntax trees will appear on this slide, so not. So this is standard technology for describing the grammar, concrete grammar of our input. And for humans, it's easier to learn it through examples. So at the end, we're going to have some examples. If anybody prefers to read this, we are going to question your humanity. So, yes, so let's see. The syntax trees are described in the syntax file that you can look up. I copied it here. And this is now the abstract representation of input. This one should closely resemble, or resemble as much as possible, the thing that the user actually writes. And I think I forgot to, no, I did not forget anything. So this is what the user can actually write. This is not the type theory. There's going to be lots of movement now up and down Ambrosius levels, but it's all the lowly levels that are beneath him, right? We are just like 5 levels below what Ambrosius is doing. So this one is used to represent the syntax. I do not recommend trying to process anything in the parser. The parser should just create the trees. You will process whatever you want to process later. Otherwise, you're going to create spaghetti code, so don't do that. So, for instance, variables are still just strings. At some point, they will not be strings anymore because we don't want to implement them using strings. Another point worth making is here when you have lambda. So a lambda is going to have a variable name, a type, term, but notice the type is optional. That's because the grammar allows the user to omit the type of the variable when they write the lambda, as opposed to what we had yesterday when the lambdas needed to be annotated. That's because the ones from yesterday are not the input. They are somewhere up higher, okay? They are supposed to represent the type theory, not the input. Also, we are smuggling in additional construct that we didn't have yesterday, a scribe, which is just when a user writes a term, colon, a type. So the user can prescribe that a certain term must have a certain type. And you will see later that this is just essentially what this does is it forces the type checker into checking mode. It'll say, oh, let me check that this thing has that type. This is useful for the user to convey information. Any questions about this or how to read this thing? Yeah.
Where do you still need the addition on the lambda if you can just use description?
Okay, so that's a good question. So the idea
we have a string, okay.
Okay, so the question is this: why bother with the type here?
Maybe
If
the camel type system is not there.
No. But let me first explain your question. Okay, so just to see whether I understand you. So the question is the following: why bother with the type here when you could just omit this type, and then whenever the user wants to provide a type, they can use the ascription? And there is an answer to this. So do you know the answer?
Yeah, you have a string here. It's not really a syntax acquisition where you can have an expression.
It's not even that. It's you will annoy the user greatly if you do that. Because here the user only has to provide the type of the variable. But if you say, oh, I'm going to delete this, and then you're going to have a lambda, colon, and the type, now suddenly the user has to write the entire type instead of just the type of the variable. I'll make, okay, I mean, you're rolling your eyes. I'm going to make a custom version just for you where you have to do that, and we'll see how it goes. Because it's annoying, right? Yeah. Like you don't, like you want to give the user, we have to think about being user friendly. So you have to allow the user to provide the thing they want to provide without suffering too much. So in this instance, I will allow the user to provide the information just about the variable without having to write down the type of the entire term. Yeah, just consequence. Yeah. Okay. Did I answer the question? Yeah. Okay. Oh, one other thing. Notice that we have terms and types, but they're the same. That's because at the level of the input 6 syntax, you can't really tell whether you're looking at a type or a term. You see a variable. Well, it could be a type, it could be a term. This is not something you would want to try to figure out during parsing. Now, if this was 1980, then maybe all the variable names have a $sign in front of them because you are programming in BASIC or something like that, or the language is very restricted, so you can tell from the position that it needs to be a type. But we will not even try to do that. Whether something is a type or a term in our language is going to be determined by type checking. And especially since we have type in type, everything is kind of jumbled together anyway. So that's why we say they're the same. But there is use for having two names for the same type, because that's helpful to me as a programmer, because now it says type here, so it's a product of a type and a type, whereas a lambda has a type annotation and a term. And it's really useful to read these definitions so that you have this type term distinction, even though formally they're the same thing. Yes?
Does it also help us while programming to not confuse the two, or are they just interchangeable names?
Yes, so right now they are interchangeable names. When we will revisit this when we get to the internal representation, where we really don't want to confuse them, and we'll see what we will do at that point. Okay. There it would be dangerous to confuse them. So we want to avoid that as much as possible. And we want pilot support. Right? So whenever you find yourself thinking, you're writing some code and you're thinking, oh, I'll just be careful. Stop right there. You will not be careful. Programmers cannot be careful. No. Okay. Okay, so let's look at the internal representation. We're going through the representations. So now it's kind of similar, but let's first address your question. So we have terms and we have types, but the types are explicitly tagged with a constructor. So that when you write down a term, it cannot accidentally be a type. I must always be aware of the fact that I have a type because I will have to tag. This is not the most pure possible implementation, because I'm saying that you can take any term and tag it as a type, but that's clearly nonsense, because for instance, lambda can never be a type. So if I were super pure, I would now have another definition, which would look almost like this one, but it would have to be without lambda. But then I would have to use two different kinds of bars and two different leds and everything. So there would be prod as a term, and then there would be a different prod as a type. So everything would get duplicated. This can possibly buy you some points when you go to the type theoretic heaven for being such a nice person and separating terms and types. Depending on what you're implementing, you might want to do that. We're not going to do it, and we'll just be a little bit dirty here at this point by equating them. Because we have type in type. If we didn't have type in type, if we, for instance, separated types from kinds, it's very unlikely that it would say that kind is just a type, okay? Because that allows confusion that we want to prevent. But we walked into this type in type, so we're going to do that. Okay, next, if you look at the variables, they're not strings anymore, they're vars. But what is var? Well, var is down here. So this is now starting to use bindlib. Not going to say too much about bindlib, but I'll try to say enough so that you get a feel for what's going on. So bindlib is a library that's going to take care of bound variables for you. If you've never implemented de Bruijn indices with your bare hands, you should try it once, okay? And then you should read bindlib documentation. There's almost no point in using the library once. It's the same for the parser generator. You should implement the parser with your bare hands once. Anyhow, what does bindlib do? So it can take care of bound variables for you, and so it has its own data type of variables. The TM here means that we're telling bindlib that these kinds of variables will refer to terms and that they may be then bound. So we are binding terms. Indeed, in our type theory, it's the type variables, the term variables that are bound. Really have, right? Okay, so that's just that we're using bindlib's notion of variable. Whatever it is, it's taking care of everything for us. Then we have these binder things here. So whenever you have a construct that is going to bind a variable, you should use bindlib's binder, which is down here. It takes two parameters. One of them we keep arbitrary, and the other one is saying we'll be binding term variables. So something that ranges over a term variable. So for instance, a product will bind a term variable in a type expression here. There's no more name for the variable. Well, there's no name for the variable here because it's going to be hidden inside the binder. So the binder is also taking care of the name of the variable. Yes, question?
So in the definition of TM, there's a sort of like TM is parameterized by some binding library. So for instance, you have the syntax TM space bindlib.1.
This?
Yes. So it's sort of like, but in the definition it says type TM is equal to. So sort of like, is there a syntax? If it was a Haskell program, I would say type TMA is equal to.
Yes. So you're a Haskell programmer, but not a Camel programmer.
Correct.
Okay. So I have some very bad news for you. In ML, they write type constructors the wrong way around. So they don't write list A. They're insane. They write a list.
Okay.
Yes. So this to you should mean binder applied to TM.
Thank you, sir.
Yeah. I once heard an explanation of why that is. Because it's an integer list, it's not a list integer. But I think that's a very weak
Okay, sorry. Yeah.
Okay. Other questions? Like, so you can see it here. So to more specifically answer your question, TM is not parameterized.
That was
binder is parameterized.
Yes, that was why I was.
It's here. It's backwards.
Yes,
yes. And
makes sense.
also because it's backwards and insane, the parameters have to have a back quote in front of them. This is so that you can imagine how nice life would be if this were a Greek letter alpha.
Right.
That's the purpose of this factor.
Well, and maybe also so you don't look at him.
Also not, possibly.
It's the verb.
Yeah. Okay. Any other Haskell related questions at this point? Yes.
What's the type of spy and term?
Which line are we looking at? This one?
Yes.
Do you understand these lines?
So?
Like they are constructors of an inductive type. What would happen if I only had one line? And if I deleted all the lines except the first one? I would still have a weird inductive type that only has one constructor. Well, that's what this is. This is an inductive type, but it only has one constructor. So the only purpose of this is that if you want a type, you have to write tie in front of it. And this is keeping me honest about not confusing types and terms. I am hoping dearly that OCaml is going to optimize this away, but who knows? Yes?
Is there a bind label for Haskell?
Is there binding for Haskell? I would imagine there might be at least 3 of them. Yeah. Does anybody know if there binding type thing for Haskell?
Yes, there's.
There is. Is it at least 3 of them? Probably.
At least two.
At least 2. Okay, he knows about 2. Yeah. Okay. Yes. The answer is yes.
We want the names.
There's a bound and an unbound.
Yes.
Oh no, there's the packages that are called bound and unbound.
Yes.
How innovative.
But there is also a library called data.bind.
Okay, there you go. We've got 3 of them. Okay, how about contexts? So if you're using De Bruijn indices, you will be tempted to implement contexts using lists. And that sounds slow because when you want the 7th De Bruijn index, you will walk down the list and you're going to have linear time access. But I should warn you that that may be slightly counterintuitive. If you have 10,000 variables, yes. But so long as everything goes into the primary cache of your CPU, you might not care. Because getting one memory location out of your memory and getting it into your cache, in the meanwhile, you can probably process 1,000 variables. So, it's tricky. But what's tricky is predicting the efficiency. It's better to measure efficiency than to try to predict it. Anyhow, what we're going to do is we're going to use, we don't have lists, we don't have De Bruijn indices, so we're just going to use maps. So OCaml comes equipped with a standard library that has a data type of maps that are implemented using balanced trees probably, so everything is mostly logarithmic. So we're going to have 2 kinds of maps where the keys are strings and the keys are variables. This TT refers to type duty to the thing on the previous slide. So the variables defined in the core. And so then a context, here's another insane thing that the OCaml people do. They name every type T, which is lots of fun. So you get a module and then you say, oh, I have a type, you call it T. Then if you have a second type, you word it. But so long as you have just one, you call it T. So we're going to have a type of context here written as T, but everywhere else it will be referred to as context.t. See how smart we are? Okay, so it's got 2 components, a map that takes strings to variables. So that's just used to map the input syntax to the variables. And then this is the real one, that's the real context. It takes variables to typing information. What is typing information? An optional definition and a type. Just like yesterday, our contexts had types and optional definitions. Okay, that's context. Okay.
What if the user uses a name twice while...
Right. Thank you for reminding me, because that's a question we should address. So this is called shadowing. The user might write lambda x, something. And so now we have x twice. So when we have x twice, then we'd say that the second x shadows the first x. The first x becomes inaccessible, right? You can't get to it anymore. So we have to think about what's going to happen with these things. Well, these are functional data types. And so the maps in OCaml, if you update x, string x, if you update it, you just get a new map. And the old one disappears, so it will have the correct shadowing effect. So I don't have to worry about that. Yes. If I were in some insane language where I had stateful maps, that would be an entirely different business. But I don't want to be in a stateful language like that. Okay? Any other questions? Okay, so what's the core functionality is, well, type inference and type checking. So let's think about this. Let's first think about what it's even supposed to do. So here is the first approximation of what inference does. It's going to take a syntax term as parsed. The user will write some nonsense like type apply to type, will parse that into a string, into a tree, that's it. And then we'll take a context, and now in order to infer this, we have to produce a type. So we'll produce a type, but not just a type. We also have to produce this trusted core term, right? Because we are mapping input to the core type theoretic judgments. So this one, we also have to do it. So we are processing terms to terms, but also computing types at the same type. Is that clear? Is the same type. Is that clear that we need to do this? Okay, both of them. Okay, so how about checking? So checking similarly, now it's going to take syntax, a syntactic term, so input syntax term, a type that has already been certified. So this is not syntax type. This is a type that we already previously checked. You will see how the top level, when the user writes something, or when we have a description, we will first process the type, make sure that it's a type, then we will check the term. So you don't want to check syntax against syntax. You want to check syntax against something that makes sense, okay, already, so that you know that your type is already okay. And then you take a context. And yesterday I said in inference, the type is the output, but now we also have the other output, which is the process term. And in checking, we said, oh, it's just a Boolean, just either succeeds or like you type check and there is no output. There are two inputs, so the two inputs and this context. But now we also need to produce a checked term because we need to take this term and process it and give a certified internal term. There is an output here. You might be wondering, why am I not outputting a type? But that doesn't make sense because, I mean, the type is already there. Why would I output the same type again? I have no need for that. So I'm not outputting the type, just the term. Yeah, questions? Go on. Now, this is like, in the ideal world, these are functions that would work like this. But really, they can also report errors. So that's not visible in the type because we're in OCaml. Errors are going to be implemented using exceptions, and exceptions, the fact that something is raising an exception is not visible in the type. If this were Haskell, at this point, we would definitely have exceptions, a monad, exception monad visible here. So we're going to learn from Haskell to use these monads to our advantage, but we're going to be a little less puritanistic. In Haskell, the monad always encapsulates all the effects. Well, in OCaml, some of the effects are built in, like input, output, printing, exceptions, and so on. So we're just going to encapsulate the part of the monad that we're interested in and that the OCaml does not provide. So to understand that, first notice that it's a little weird that I am providing context as the last argument. Okay. Normally you would expect, well, if you're inferring something, it's context, v dash, term, right? Context is in the wrong place right now. There's a reason for this. When you implement inference and checking, you will have to keep passing this context through, right? Yeah, you say, oh, I have an application, I have to type check the first argument, or infer the first argument, I have to pass the context. Then I have to type check the second argument, I have to pass the context. So you're going to have a lot of boilerplate code where you keep passing the context. And then one day you're going to say, oh, but apart from context, I also want to pass universe information. And then you will have to go, and in every function call, you will have to add, oh, I'm also passing some universe information. And this gets annoying. So it's better to have a bit of use a little bit of abstraction at this point, so that later on, if you change your monad slightly, if you change your environment, how it works, you don't have to rewrite all the code. In fact, we will do that tomorrow. So what you do is this. So define a auxiliary type, which is just says a function from context to a where a is arbitrary, and I just stick this m here. So I just introduced an abbreviation so far. Okay, nothing happened. But this M is a monad. Who has used monads as functional programming? Okay, most people. So if you know monads, you know monads. And otherwise, think of this as a smart hacking, I think, is a good first approximation to monads. So I'm reorganizing my code so that it looks nicer. Okay, that's why you can think of it. I will not attempt to explain monads in 5 minutes. I think that's a mistake. Another mistake one can make is to write a blog post about what monads are. That's also a mistake. Don't do that. Who here has written a blog post about monads? Okay. Okay, so how is this a monad? Well, a monad wants to have a monad. What you need to do is you need to describe binding. And in OCaml, binding is written with let star. That's do. The Haskell's do is let star. We'll see the code later. You'll see let star, let star, let star. That's do. Okay, so you are trying to bind C1 into C2, and we're in the reader monad. This is a reader monad. So I want to compute this using this context. Then when I get the result of this, I want to pass it to this thing. Okay, so let's do it. Compute C1 in this context, pass the context to it. You get a value, pass the value to C2 and the context. This is how you combine it. So this let star notation will implicitly pass the context through everywhere. I will not have to write CTX, CTX, CTX everywhere. It's the same thing as bind. It's literally the same thing. And how do you return? How do you have a pure value? If I have a pure value that doesn't need the context, I just return the value. I ignore the context. Okay. So that's a simple monad. But the point here is that we can make this monad fancier. If you were in Haskell, you would add exceptions to this monad. And maybe you want something else. Maybe you want meta variables, and then it becomes fancier. Or you maybe want user input, interaction, whatnot. So one way to think about these things is to say, my proof assistant is a kind of a monad. It's one way to say it. It would make a really nice blog post, because it would be a blog post about proof assistants. It wouldn't be about monads. Okay. So at this point, it's best to just read the code. We're not going to read all of the code, but I would like to convince you that it's not that hard, because I have these counts here. Okay. So that's not a lot of code. You can survive this. It's like less than 500 lines of code. And it's commented. There are comments. Okay, so that's, in these in the lines of code counts. Is there a tool that will count lines of code, but it will count comment lines as -1? Because I would really like that. Because then I can have zeros on my LOC. I think I would deserve it. I think it's fair game. For every comment you write, you get to subtract a line of code. So these are the main files that will perform the obvious things. This is functionality regarding context. It's just like looking things up and so on. And this is the type checking, has inferred check. This is normalization. This is equality. So we're not going to read all of this, but let's have at least a look to see if this is recognizably the bidirectional type checking that we had yesterday. Is this big enough? Maybe make it bigger. Okay. So this is the type checking. So first of all, there are some possible errors that we want to report. So we declare them. This is a function that will print out the errors so the human can understand it. We open the context monad so that let star does what we want. So we have infer. It's a little bit suspicious because it has an underscore. But in any case, its type it does return term and type with the strange underscores. So we need to address the underscores, but let's ignore them for the moment and see whether these look like inference rules. So if we are trying to infer a variable, we should look up the identifier, that is to say, we have a string. First, we see which variable this string is. If it's not something we've seen, the user made up a variable that doesn't exist, so we tell the user we don't know what this is. Otherwise, we look up the type of v, and then we return the type, and something funny is going on with lift here, and then we return the variable, and something funny is going on with the underscore. But if we ignore the underscores, this is the thing we expect. We started with a string, we're ending with an abstract variable, and we have its type t. So this does look like a rule, the rule for variables. Okay, so let's not do everything. Let's do one more. Let's do lambda because it shows you something interesting. So there are two lambdas. One lambda is where you have no annotation. If I'm in inference mode and the user did not annotate the variable that they are abstracting over, then I'm going to complain that I don't know how to infer the type of the argument. Now, better proof assistants are better in this, and they will try harder. We will immediately fail. So we would want to have something better here, and we're going to work towards it in the next two lectures. But right now, we just die. If we do have the type, then what do we do? So this is an uncertified type. This is user input. So first, we check that U is a type. So check type here. Check type just checks that T actually is a type. And you see how I've forced myself to write tie in front here, to say type as type, not as term. So this is just an auxiliary function checking that T is a type. Okay, so let's see, where were we? Here. Okay, so first we certify the type. So now our U, I'm shadowing U. So this is a programming practice which I rather like. U here, this U is the input syntax. This U is the input syntax. And once I processed it, I know that I never am going to use it again. So the output that I get, I also call U. So now this U is shadowing the previous one. So from here onward, U is the certified one. And this is a conscious choice. It's a programming style. I'm not saying everybody should follow it. I'm just explaining why I'm doing this. I'm doing this so that I don't accidentally try to use the old U. I'm indicating to myself, I'm done with the old U. Here comes the new U. And now what do we need to do? Now we need to do something about E. We need to infer E, which is here. Infer E. And we're going to get a certified term and its type. And then we're going to construct the lambda. But we need to do this in an extended context, which is what this thing does. Okay, so there's something in the context that is going to change the context environment by expanding it with a new identifier X and a new variable of type U, and it's going to pass the abstract variable to me. It will say, oh, I'm creating a fresh variable for you, I'm extending the context with it, here's the variable I created, then you go on, then you see what point. That's it. Okay. So it really is just transcription of the rules of bidirectional type checking, but with all this stuff around about variables and a little bit of an error reporting and things like that. But in essence, it's the same rules. We should test one thing. Yesterday, I emphasized that there is only one place where the rules use equality, right? It was switching from checking to inference mode. So if that's true, this file should only refer to equality once. Does it? Yeah. This is the only location where equal is referred to. And where is it? It's in Oscar. Oh, let's see, be careful. Where is this? This is in checking. Okay, so let's have a look at checking. So checking is going to get an input. So the input is this. This is the syntax input. This is the location. I'm taking apart the location from the data. We've got a certified type, and we're supposed to return a term. So we look at our syntax, and we're checking whether E prime has type type. There are two cases. No, there are three cases. There's one case for an unannotated lambda. In this case, I want to convert my type to a product, something we have not addressed yet, and then proceed. And I'm not going to look at this. I'm just going to look at type checking in general. So one case for unannotated lambda, because I want to propagate the information into lambda. Another case for let, because I want to propagate the information into E2. And a third case for everybody else. So what is this everybody else? An annotated lambda is inferring. An apply is inferring. A product is inferring. This is syntax driven. I'm looking at the syntax, and these are all the cases that are inferring. And a scribe is also inferring, by the way. So what do? I infer because it wants to be inferred. And then I check that the type that I inferred is equal to the type that I got. So this really is the rule for switching between modes. Yeah. Okay. Anything else we should look at? Yes.
Do I understand it right that we use OCaml's binders to represent the object languages binders? Line 121, for example.
20.
21, or also in the lambda.
121 or 21?
121, yeah.
Here.
Also 112, yeah.
Ah, okay. So let's look at this. Okay. So here's, okay. So first of all, don't look at the code yet. Let's just think about the problem that we need to solve. Some of the rules say that I need to check something in an extended context. Yes. Some premise says extend the context with X of type T. Okay. How are we going to implement that? We need to take the context and extend it. But in our case, now it's going to be a little more complicated. We have a concrete string. So first, we need to create an abstract fresh variable. Ask bindlib, please give me a fresh variable. Then I need to associate this string with this variable. Then I need to take my context, extend it with this variable of a given type, and proceed. So how do I proceed? Well, that's some function that's going to do something, but this function needs to know what variable got created. So I'll pass the variable to the function so that whatever it wants to do with this variable, it can. So this is what this is saying. So this is saying, hey, I want you to extend the context using this identifier with this definition, even in this, because it's a let. And it has to be of this type. And after you have done that, use the inside that context in the reader monad. This is the reader locally, or to know Haskell, locally. So in that context, run this computation, but this computation may need to know what to do with V. For instance, it needs to bind it or something. So it needs to know what it is. So it's not like LF, if that's what you're thinking, where I'm somehow reusing OCaml's bound variables. That would be a different thing. That's sometimes called higher order abstract syntax, where I'm just using OCaml functions. I don't do that. I can't, I mean, I could do that, but I'm not doing that. Let's maybe look at, look at this one. I think we have plenty of time. What does it look like? This width ident. Does it do what I promised it would do? Okay. So you get a string, you get a possible definition, you get a type, you get the thing that needs to happen afterwards. I need to run this C in the extended context, and I have my context. I create a new variable. And so using the hint that this variable, when it's printed out, should be called X, if possible, and otherwise some X1, X2, or something like that. Bindlib will take care of that. I extend my log context, and then I run C, passing it VM to extended context. By the way, if you read this, you should first read the MLI in OCaml. ML files are the implementation files, and the ML files are the interface files. And I highly recommend that you write the interface files, even if you're the only user of your code, because after a while you will thank yourself that you have the MLI files, because then you know what's going on. Yes.
So in this course, we care a lot about speed. And what is actually the computational complexity of this bidirectional type checking algorithm? And is it optimal in some sense?
Probably the worst case is pretty bad, I would imagine, as it usually is.
I mean, if I generate constraints and check them, the worst case is O of n squared.
Yeah, I mean, the
Right,
thing
it's
you
the number
really
of
have
variables.
to be a trade-off is normalization.
Right.
So it's the quality checking that people usually worry about more than just the bare bones type checking. I mean, if you're going to optimize something, you should work on equality first. And then when that becomes faster than bidirectional type checking, then you should implement bidirectional. Then you should optimize bidirectional.
Okay.
But you saw that it's mostly kind of like just a structural reduction. You just go through the syntax and you do your thing.
Right.
So you wouldn't expect it to be horrible.
Right, but there's no formal result that's.
Oh, I'm sure there are lots of formal results. I didn't know that.
Okay.
Does anybody else here? They know if you know them papers, please tell us afterwards. Okay. Questions?
Question related.
Yes.
In your experience in implemented things, to which extent these worst case complexity results have stopped you from getting things workable programs?
Okay. So people who have done large scale processing of formal stuff, so for instance, Frederick, have a lot more experience with this. And I think what happens is okay, I'm going to say it like this. If you have a lot to process, like if you're a rock and you have huge libraries and so on, right? Then it will be worthwhile optimizing, and people do optimize these things, and they care about it. And so there are two kinds of optimizations that you can do. One is you just have a better you just have sort of you optimize things so they're better organized, and that's going to start showing by giving you some constant factor speed up. You know, my substitution is now 3 times faster, okay, because I did something. But there are also cases where you see that something inefficient is going on. Like for instance, I'm going to I will literally implemented spine check way that was presented yesterday, but that's suboptimal because you first normalize and then you compare spines. But maybe if you already had spines that you could normalize, but they happen to be equal, you didn't have to normalize, and there are lots of tricks like that. So people actually care about this in production, sort of industrial strength proof assistance, but I don't know how to answer better than that. I'm not aware of formal studies of complexity other than stuff like, hey, there's this bizarre case of Hindley-Milner that's doubly exponential that nobody will ever write. You know, of course, somebody writes a tool that generates code like that. But yeah, so I don't know. It's, Frederick, do you have anything, any comments to say other than?
The complexity of time checking is bounded below by any function from NAT to NAT that's definable in this set theory. So
Oh, well, okay, so that's a good point.
the
This has to
complexity
do.
of set theory checking is about the fastest growing function
Yeah.
that I know how to describe.
I mean, that's because it's relative to the fact that you're going to normalize things. So, but this is a good way to say it. Okay, in my proof assistant, I can define some function from NAT to NAT that takes forever to evaluate. Then I make my type checking depend on the result of that function. So it's going to take forever because in order for the type checker to compute whether the types fit, it needs to calculate the function. So it's going to be horrible. in that sense. Thanks. Yes, that's a useful remark. Let's look a little bit at equality. Inequality. I just want to check that I have the function that I was promising. Okay. So, okay, we have compared terms at a given type, where E1 and E2 are terms and ties type, and then blah 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 blah. Well, it's not a lot of blah blah blah. It's normalize the type. See if you got a product. If you got a product, apply function extensionality. Otherwise, proceed to the normalization phase. And if you get a lambda, something is really, really wrong. Okay. Let's go back. And then there should be normalization phase. Where is normalization phase? Okay, normalization phase. Normalize E1, normalize E2. The normalization phase does not have any typing information. Compare them. If they're both type true. If they're both product, compare structurally. If they're both lambdas, something is really, really wrong. Because that means that the extensionality rule didn't work somehow. So this should never happen. I highly recommend that you cover all your cases, and the ones that shouldn't happen should make your computer produce blue smoke, so that you know that something is wrong. That's a lot better than the computer just going on and pretending that everything is all right. Oh. Okay. And then spines. Here are spines. Are two spines equal? So we normalize things. Oh, maybe let's look at the normalization. So when we look at the normalization, there is one thing worthwhile doing. Okay. What would you think the type of normalizing is? So to normalize a term, okay, you want to take a certified term. You really, really want a space in front of this arrow. I apologize. You want a certified term, and then when you normalize it, you will get also a term, but it will be normalized, but it's still a term. So should we return a term? We're not returning a term, because here, you see, it doesn't say TT term. This TM refers to this one. So I have a special data type that is just for weak hand normal terms. So it's either a type or a product or a lambda or a spine. And if it's a product, it has two unnormalized types. If it's a lambda, it has unnormalized components. If it's a spine, it's a variable with lists. And why am I doing this? Because this way, OCaml helps me. Now, when I normalize, I know that it's one of these four cases. It's impossible that it's say, a redux. It cannot be by design. And so this is very helpful. You should write your programs defensively. Maybe another way to put this is the following. It's okay to have a lot of data types, auxiliary data types. Have a lot of data types that provide just the information that you need. So here I have a special data type for weak hand normal forms that is exactly the information that I think it should be. And so that means fewer assert false in my code, and I'm happy. Or at least the assert falses are concentrated where they should be. Yep. Okay, let's go on here. I think how am I doing? I think we can, yeah, started it to, yeah, we should go on. Okay, so how do we put it all together? Well, there's going to be some sort of a top level. So let's just see what the top level can do. I just imagine a simple top level. Okay, so you can load a file. And obviously the correct extension is FTT for fault activity. It shouldn't be anything else. You can declare a constant of a given type. It's an undefined constant. You can do that. You can define something. And there are two kinds. You can have an unannotated definition or an annotated definition, where you also specify the type. If you use this one, it will infer the type from E. If you use this one, it will check that E has type T. You can also just write down a term and infer its type if you want to, just for the fun of it. And I included evaluation, and this is called by value evaluation. So that's more like OCaml. Evaluate eagerly, not weekend normal forms, but completely. So it will give you strong normal forms. I think so. Yeah. Then there is some main executable which takes care of command line options and such, and I'm not going to drag you through that. In a way, you can see that some of these things correspond to the global top level things correspond to the local things. So the top level is just like open-ended local definitions that never get out of scope. So this is like extending a context. This is like a local definition. Well, these are weirder because these are somehow computational things that happen that are not part of the type. Maybe they're about the environment. Questions? Let's look at an example. If there are no questions, let's do church numerals. Okay. So here's some OTT code. A church numeral is defined. So the number n is defined as n-fold composition. And so what you do is, given any type, you take an end of function from A to A, and you return a new end of function which is composed with itself n times. So 0 takes the function and does compose it 0 times, so it just returns x. And then here are the standard definitions of successor, numeral addition, and multiplication. So maybe let's look at an addition. So plus is going to take a numeral, another numeral, and return a numeral. And by the way, arrow is a shorthand for pi. It's the like usual. Okay, I forgot to mention that so far. It's syntactic sugar. So you take a numeral n and a numeral n and a function f, and now you're supposed to iterate f n plus n times, which is just this. You take f, you iterate it n times, and then on that result, you iterate f n times, and it's going to be n plus n. And then if you think about it, this one is going to iterate n times an n iteration of f, so it's going to be n times n. So this is going to evaluate 1000, which is not shown here. I can show you the actual file. Okay, so I also have 2, 1, so on. So here's 3 written with bare hands. So number 3, so if you've never seen church numerals, pay attention. So I say, I take f, and I need to produce f composed with f composed with f. That's number 3. It's 3 because there are 3 f's here. If you want 7, you write 7 f's. Then 1000 is defined as 100 times 10. And 100 is defined as 10 times 10, and 10 is defined as 5 plus 5. And so when we evaluate this, what happens? Will it be more or less than 5 seconds? It's going to reduce these things, call by value, all the way. It's going to be a bunch of S, 1,000 S's applied to Z.
Less than 5 seconds.
Okay. Does anybody give me less than 2 seconds? Sure. Does anybody give me less than 1 second?
Sure.
Sure. Half a second. Yeah. Okay. Give me a better number.
Half a second.
Half a second. You think it's around half a second?
Yeah.
Takes a second.
It's 0.09 seconds. So, you know, computers are fast. It's kind of fun. It's boring. So let's see if this is 0.9. something happened. Now we're in trouble. I'm in trouble. You want to see something even worse than that? Okay, that's too optimistic. So maybe we should do 2 here. Yeah, not linear. Yeah. Okay, but I mean, these are unary numbers. This is a silly example. I think I'm done for today. So what are the takeaways? The takeaways are that, first of all, it's not a lot of code. You can also do this. That seems like not enough. Oh, I have to go further. Now it's too much. Okay. Let's do this. This is most of it. So, which ones are the longest ones? These two guys, what's this? Type checking is 200 lines, and concrete syntax is 200 lines. And the rest is kind of okay. So, of course, if you want to get a real thing, I don't know, we should count, do I have it here? That's probably more. How do you do this? Find dot name. And then what? X are something like this. 17,000. Which is not a lot. I mean, in Java, this would be 100,000. But also your IDE would write 3 photos of it. There are some exercises at the end. Okay, the exercises are, of course, that you can try to play with this if you want to. Oh, there are a couple of questions. So we solved number 3. If you look at the let, the internal load definitions of let, they store the type at which of the local variable that is being defined. So the exercises, which is not something that we had yesterday. Yesterday, in our typing rules, we didn't have this. So the question is why, and the way you should answer this is by finding the place in the source code where this type is used. And it'll answer why. And the same thing for, we have type ascription. By the way, type ascription does things like this. Let me show you. Oh, one useful thing is this little utility gives you landmines editing. So you can do this. Let's have a type. Okay, it's unhappy, doesn't matter. If I say, what is the type of this? It's going to say, I don't know. But you can say, but I know it's of this type. And then it'll know. So this is called type ascription. You see that function spaces are not nicely printed, but okay. So this is called ascribe in the rules, in the slides. And so find out the rules, but reverse engineer them from the source code. Look for all the places where it says ascribe, and you will see that it's somewhere in the normalization, there's something in inference, checking, see where they are, and reverse engineer what it is. Okay, I'm done. Any other questions? Okay, so we have a break for half an hour.